Hello and welcome in. In this video, we're going to be looking at intermolecular forces, how they affect the properties of our substances, as well as the phases that our substances exist in. Intermolecular forces are what exist between one molecule and the neighboring molecules. And in general, these forces are going to be attractive. These are the forces that keep one particle stuck to another particle or close to other particles. We have these slightly attractive forces that allow us to have phases beyond just gases. If there were not these intermolecular forces, then we would get to have all of our substances just spread out, bounce around the universe, and really just ignore each other. Instead, that's not the case. And we know that we do have solids and liquids, these so-called condensed phases, where our particles do get to stick together to some extent, depending on maybe the relative amount of energy that our particles have and the relative strengths of these interactions. We might expect some substances to be solids at room temperature, some to be liquids, and others to be gases. This is going to be the balancing act that we consider. We want to think about kind of this scale where we might have a certain amount of energy for our individual particles. This energy, as we know, is related to how hot our particles are. Kinetic molecular theory applies for all three phases. As we get to higher and higher temperatures, our particles have more and more energy, which will allow them to bounce around and ignore each other. On the other side of our scale are these intermolecular forces, abbreviated IMF. These intermolecular forces are going to be our attractive forces that keep our particles stuck together. And so these are competing factors. If we have strong intermolecular forces and low amounts of energy or low temperatures, that means we would expect to be these condensed phases. On the other hand, if we have lots of energy, if our substance is very hot, or if we have weak intermolecular forces, these particles are not held together very tightly, then we might suspect that we'd have the more gaseous states, phases that are not condensed. This is always going to be that balancing act that we consider, how much energy compared to how strong our intermolecular forces are. And we can think about how this comes into play down at that atomic scale. For our solids, our particles are held tightly together. They are packed closely together because they either have low kinetic energy or because the intermolecular forces keeping those particles together is very high. So some combination of low energy and strong intermolecular forces will tip this scale towards the condensed phase. As we have liquids and gases, well, maybe we have more and more kinetic energy, enough to break away from the other neighboring particles and move on into these other phases. Alternatively, if we're comparing one substance to another, maybe there are different amounts of intermolecular forces, which makes it relatively easier or relatively harder to go to these less condensed phases. So for the rest of this chapter, the rest of this unit, we'll be considering this balancing act. How strong are the intermolecular forces for this substance? And how much energy do our individual molecules have? We'll use this idea to try to decide some relative properties of our substances. As we have different amounts of intermolecular forces, this will affect some properties such as the boiling point of our particles. the melting point of our substance, the enthalpy of vaporization and fusion, as well as some other physical properties we can discuss. In general, we can say that as our intermolecular forces get stronger, as the strength of our intermolecular forces increases, we're going to see a certain effect on our maybe boiling point or melting point. If we're thinking about the boiling point, our intermolecular forces are keeping things held together. And so we're going to have to maybe put in more energy in order to boil. And so our boiling point temperature will have to be higher. Likewise, our melting point. In order to melt, we need to put in energy to break these atoms apart, these molecules from each other, overcome those intermolecular forces. If we have stronger intermolecular forces, we're going to melt at a higher temperature. And so our melting point might start to increase. If we're thinking about enthalpy of fusion or enthalpy of vaporization, this is how much energy is required to melt or evaporate our substance. So not the temperature that it melts at, but the energy required to do this process of melting or evaporating. Well, likewise, the stronger our intermolecular forces, the tighter these molecules are holding onto each other, the more energy is going to be required in order to melt or evaporate. We have one last property listed on the slide. Well, actually not even listed on the slide, but our vapor pressure notably is going to have the opposite trend. Vapor pressure is the pressure of the gas that forms above our liquid. If our intermolecular forces are getting stronger, it is harder to evaporate. We're going to have less gas above our liquid, and therefore our vapor pressure is going to be lower. Fewer particles above the liquid lead to a lower value for our vapor pressure. And there we go. This is kind of our broad overview. We have this idea of intermolecular forces, our particles attracting to each other at least some small amount. We can have this balancing act between the strength of our intermolecular forces and the relative amount of energy per molecule or per atom. And we'll use that idea to help give us intuition about many properties of our substances. That's it for right now. In future videos, we can look at what these individual intermolecular forces might be and their relative strengths to help draw these conclusions. So stay tuned for that. Thanks.